Okay. Oh, okay, perfect. Okay, thank you all. So, I think last year I wrote this post talking about the future of Ethereum, and one of the things that I mentioned will be very important to the future of the Ethereum protocol, and anything built on Ethereum in the long term is advanced cryptography, right? And I think the big change that we've seen in cryptography over like the past maybe 15 years is that 15 years ago we were talking about special purpose protocols that were designed for specific applications. Like there was a signature protocol, there was a blind signature protocol, there was a voting protocol, there was this type of identity protocol, there was this other type of identity protocol, and it was really practical to build things, because to build anything interesting you have to be good at applications and you have to be like a very top 1,000 expert cryptographer. And the change that we now see, right, is that cryptography works over computer programs. And so you can have these cryptographic protocols that are extremely powerful because they are general purpose. You can just put any kind of application into them. And there's these three big ones that I talked about in the post. I compared them to the Egyptian god cards from Yu-Gi-Oh! Because I think these are just so extremely powerful, right? And it's ZK Synarchs, fully homomorphic encryption, and obfuscation, right? And I actually personally don't like the name IO, because for me IO is input output, so I just say obfuscation. You can say what you want. ZK Darks, they let you prove anything about computation that you do. And full homomorphic encryption lets you do computation on encrypted data. And then obfuscation, it lets you basically convert any program into an encrypted program that does the same thing, but you can't see the inside, right? And this one is actually the most powerful, because if you have obfuscation, you actually have basically everything else. Actually, you have, I think, basically all with obfuscation and hashes, you have like all of cryptography except TEs. And then if you also add quantum computers, you can also replace TEs. So it's very powerful. Now, for Synarchs first, right, there's two types of use cases of Synarchs. There's scaling use cases, and there are privacy use cases. So starting with the scaling use cases, I think the big one that we've been focusing on almost from the beginning is proving the chain, right? And you can think of this at L1, you can think of it as L2. At L2, it's actually the very same type of concept, right? You process a much larger number of transactions, because you instead of needing everyone to verify all of the transactions themselves, you convert all of the transactions into a proof, and then everyone only verifies the proof, and this is much cheaper. And then now, actually, we're seeing more and more roll-ups exploring switching from optimistic proving to ZK proving, which I think is actually very good. And the reason why it's good is because with optimistic proving, you need to wait for this 7-day challenge period for someone else to provide fraud proofs. And waiting for 7 days to withdraw is like it makes providing liquidity very expensive. And so we're starting to see all of these centralized bridges and the layer 0 and chain like CCTP and all of these things. And a lot of these things, they introduce many more trust assumptions that we do not need to have. But if we want to actually do bridging without trust assumptions, then we actually need it to be instant or close to instant to move assets between L1 and L2. So I think we need ZK for that reason as well. On L1, we can have universal and ultra efficient clients. So you can have a world where everyone, including browser wallets, including mobile phone wallets, including IoT devices, everyone is verifying the chain by default. Right now, if you want to run a full node, it's okay, you need to have 1 terabyte of data, and then most people's computers don't even have 1 terabyte, and like it's complicated. It's a choice. It has high effort. Verifying the chain will become like basically instant, and also you can even have much more efficient full nodes. So this one's one of the things that we've been starting to look into that I think is interesting is this concept of partial state nodes, right? So today, there's basically two choices that you have for interacting with the chain. Either you have a full node or you trust the RPC. And Helios is like starting to become available, and like that actually that gives you light client verification for the chain. But actually, even if you have a light client, then there's still one way that you have to trust the RPC, which is for privacy, right? Even if all of your queries, they come with Merkle proofs, even if they're verified, you still have to trust for privacy. And so we have a lot of interesting ideas that we're working on for decreasing that, but the easiest, the most practical way to not have that problem at all is if you have a full node, if you have all of the state locally. So one thing that you will be able to do, actually, this is, I think, possible to do like almost not quite today. I think by the time Glamsterdam, which will include block access lists, comes to Ethereum, I think it will be possible to do this in a hackathon. All of the tools will be there. Basically, what you will have is that a block will have this like object, a list of addresses, storage slots, a list of everything that gets changed in that block. And so what you can have is you can have one snark, a proof that basically proves that this list is correct, that this list matches what all of the transactions do. And then if you're a node, then you only need to verify the proof, and you need to just locally just store all of these updates. And you could have this really cool idea called a partial state node, where you can basically say, for example, I only care about these 10 contracts. I only care about like maybe like 5 ERC20s and Railgun and IntMax and maybe 3 more. And then what you do is for your node, you only store and you only update the state for that tiny portion of the state. So even if the Ethereum state is like maybe 200 gigabytes, maybe if we increase the gas limit, the state will be 1 terabyte, then you can say, I only care about this part, and then it's only like maybe 10 gigabytes. And so you can even do this inside a browser, right? So this is really cool, right? And I think this gives us many more options to have like practical trustlessness, verifiability, and much better privacy. Now, for privacy, I think there's basically two kinds of use cases here. So one of them is privacy for on-chain funds. And there's IntMax. Railgun is seeing more and more usage recently. I think this space is developing quite well. People understand it. And then there is privacy of identity, which is like proof that you satisfy some conditions, prove that you are eligible for something without revealing who you are, right? And I think like this is a use case that like I think is like actually very broad. So a lot of the time, right, when you look at this in a textbook, you're like, okay, I want to go into a bar, and then I want to prove that I'm like over 19, over 21, whatever the age is here, without revealing my name. And like, actually, this is not the best use case, because if you go somewhere in person, then they can take a picture of you, they can Google search you, they probably know your name already. Unless you want to like go around like wearing some like full suit that like hides who you are, and then you like wear a QR code that like has a proof about you. No one knows anything who you are. You're like a ghost, walk around like the Dark Knight, but you have a QR code. Look, I'm not a bad guy. You know nothing else about me except I know a bad guy. Look, and you can verify this with the plug protocol. So, but there's so many other use cases, right? So for example, like who here uses a VPN just to like access the internet? How many CAPTCHAs have you filled in the last week? Yeah, I think like per day it has to be like more than 10, right? And so what if we had a way to like basically zero knowledge proof, like, look, I am not like some account that's like running a bot farm with a million bots. Like I am a person. But you do this without revealing everything about who you are, right? This, I think, is something that makes sense for websites to accept. It makes sense for you to use. And so either like Cloudflare or someone competing with Cloudflare could actually do this, right? So I think a lot of interesting use cases on all of these sites here. Now, the way that I think about other types of programmable cryptography is I feel like I like the use case of voting, because voting is interesting because there's all of these different requirements that go into having a good voting system, right? And you can think about, and then if you try to think about how technology improves it, right? Imagine you start from the base case, right? And then let's say in this case, like for some use case, it has to be online, and then the simplest thing you can do is you just have a vote on a server. Right. If you have a vote on a server, then you have no guarantees, right? Then the server can cheat. They can make 1,000 fake accounts. They can go in. It's probably like a Google spreadsheet. They can edit the numbers. You don't know. They can see how everyone votes. You have no privacy. They can go on the spreadsheet. They can delete your votes. You have no censorship resistance. So that is the base case, right? Then imagine you add blockchains and you also add digital signatures, right? Now you have a transparent vote on chain, right? And if you remember, like back in 2013, we were saying, look, let's have voting, let's done on the blockchain, it's transparent, and then everyone knows that it's correct, it's not manipulated, it will save the world, right? The problem is blockchains provide maybe like 2 out of 5, maybe 2 out of 6 properties that we care about. So they provide public verifiability, which is good. They provide censorship resistance, which is good, which is actually very important for voting. Then, but then like that's layer 1, right? Then the next step is ZK snarks. So ZK snarks add voter anonymity, right? So by default, no one can see who made a vote. And actually, Aragon recently has been adding this for governance, which like I think is very good. Like I think there's a good reason why voting is secret in democracies. I think voting should be like more secret everywhere. Like I actually think Twitter became much more honest when you start, like this is probably the one like very good thing that happens when likes became private. And so you can't see how everyone else liked things. So it's so voter anonymity, I think, is important in a lot of ways, right? And snarks do provide it, but snarks, they also don't provide this one property that's important, which is collusion resistance, right? So what this property says is basically that in a voting system, you should not be able to prove how you voted, even if you want to make that proof, right? Because if you just have a ZK snark, then even if your vote is anonymous by default, you can always make another snark about your snark, and you can, or you can just reveal the private data, like you can prove to one other person, right? And like sometimes this is good, right? This is like how the compliance features of some of the coin privacy protocols work. But for voting, it's bad, right? Because like these days, like you can. Technology is getting very powerful. And so if it is possible to prove how you voted, then like I can go and I can make a DApp, right? And I can say, look, if you ZK proved that you voted for, the purple party in this election, then, you get 25,000 meme coins, right? And then I launch a meme coin, and then I get, a Justin Sun to push up the market cap. And then maybe I can, and then for every voter who like doesn't really care too much, they're like, look, there's a DApp. I can vote. I can get $25 of a meme coin. And then you took over a country, right? So the challenge is, though, like if this is a much stronger level of privacy, and so how do you have this stronger level of privacy at the same time as having trust? And so Macy, yeah, this was this idea that I proposed a few years ago, and now it's like actually implemented. It's getting more and more mature. It's this extra design that adds, well, like a server for coordinate that does this coordinating function. And if you implement it correctly, then like theoretically, like you do a full version, like which I think we're not there yet, but you can. Then basically, yeah, all of the other guarantees, right, including anonymity, including verifiability, including censorship resistance, they all work even if the server cheats. But if the server is honest, then like basically what happens is that you are encrypting your votes to the key of a server, and so without that key, like you cannot actually make a proof that you did not make a vote somewhere else that cancels your vote, right? So this is like interesting. Then with FHE, you can make that one of one assumption be an M of N assumption, and then with obfuscation, you can make it even more powerful, and you can do something that says, for example, anyone can compute the output, but they only learn the output, and it costs like maybe $1,000 to do the computation because the function checks for proof of work. And if you do this, then like it becomes almost perfectly secure, right? And then if you add one-shot signatures, you can add a guarantee that the computation only gets computed once, and then it's like basically perfect, right? So the more of these protocols you add, the more that the guarantees step up. So we can talk about some like different use cases of more advanced things. So two-party computation, like I personally think that we should think of 2PC and MPC as being different, because I think there are different types of things in terms of trust. Like with MPC, there's usually this assumption, like there's a committee, there's like 10 people, we trust 6 of them to be honest. But like garbled circuits, two-party computation, it works very differently, right? And there's interesting use cases. So there's the kind of the how compatible are we a use case, I think, is a big one, right? I have private data, you have private data, and then like this is, I think you can do this for like dating sites, you can do this for employment, you can do this for all kinds of things, right? And it's like there's many of these like very valuable categories here. Then you have computing on private data with a private algorithm. So I have my data. I want to know more things about my data. You have an algorithm. You do not want to reveal your algorithm to me. So all good two-party computation use cases. Obfuscation use cases. So private smart contracts, right? So with ZK snarks, you can have private money, but you cannot have private everything, because ZK snarks have this limitation that says every object that is on chain has to have an owner, and that owner has to have the decryption key. If you do not have a decryption key, you cannot do anything. You cannot do things to other people's data. And there are these like very limited exceptions, like you can do this thing where like people's balances are an elliptic curve point, and then you make a proof that says like your elliptic curve point is a positive number, and then you just add the curve points, and then this is like linearly homomorphic encryption, you can say, and then you can do a little bit more, right? But obfuscation is like the powerful one that lets you basically do anything, right? And you can basically have contracts that have private state that only release that state under certain conditions. You could have applications with like almost arbitrary privacy properties. You can do really interesting things, like if you have your own data, you can publish or give someone your encrypted data, and then you can approve specific programs, one program at a time, to do things with that data, and you approve it with one signature. So obfuscation is extremely powerful, I think, both in Ethereum and outside of Ethereum. One big one that I think is interesting is private and verifiable AI, right? Because for the computations that we want to do with data, a lot of the time, like we want to do these like powerful AI, like LLM computations, or maybe the like other kinds of like statistical algorithms that we still call AI, right? And I think the main, like, this is very powerful, right? But the main challenge here is that like cryptographic overhead is very high, right? So like, okay, who here has tried to run a like a local LLM on their computer? Okay, so it's like it's tough, right? So like you download like I've had this like very powerful computer, and then it downloaded GPT OSS 20B, and then you run it, and like for some use cases, it's like actually okay, right? Like I actually like it. When I need to like translate things, I actually find that it's faster to talk to an LLM because like the internet, sometimes there's a delay, except internet problem, the circle 10 seconds, and then like AI, if it's a local, it's instant, but it's like still expensive, right? And then if you multiply that computation by overhead of like 1,000 or 1 million, then basically you can't do it, right? And basically, I think the reason why this space has not made sense so far is that the amount of computation that someone, like basically any kind of private AI that uses cryptography has to compete with private AI on your computer. And the amount of computation that someone is willing to do for you in the cloud is bigger than a laptop, but it's not infinitely bigger, right? It's probably not even 1,000 times bigger. And so if your overhead is 1,000x, then like even if it's on the cloud, you still have to run small models. And so maybe it's probably better to just do things on your computer, right? So this is the problem. But I have this belief that I think we can make the overhead very low, right? And AI is interesting because AI is very structured computation, right? Almost all LLM workload is linear, right? Like think about a neural network in your head. You have data coming in, you have a vector size n, then multiply a vector by a matrix n squared, then nonlinear layer is size n, matrix multiplication n times n, size n squared, right? And so you have, now the part that's nonlinear, that part is very hard, right? But the nonlinear part, it's only O of n. The linear part is O of n squared. And linear things are generally very easy to process very efficiently inside of cryptography. So I think the grand prize here that I think actually might be attainable is to make ZK snarks and FHE. And if you have FHE, then you also have obfuscation once the obfuscation becomes possible. Work with a single-digit overhead on at least on big computations. And I think we can get here. And I think if we can unlock this, then like all of this actually becomes possible. So conclusions, right? General purpose cryptography is getting very powerful. Many applications, both inside Ethereum and inside the crypto world and outside it, but like still a lot to do, I think, both on core technology and on applications. So thank you.